Hello, adventurers, and welcome to Floor 11, the Hall of Whispers. The shelf you must walk, the whisper you need only breathe. Speak a name into the dark, and the dark answers in the same breath. Already, exactly, at once, unless two names breathe as one. The corridor out of the Hall of Names runs downhill, and the quiet changes as you go. The soft, ordered settle of a shelf filing itself gives way to something faster and stranger ahead. A sound like 100 names spoken at once into a dark room, and 100 answers coming straight back. The doorway opens on a wall so vast you cannot see its edges, and it has no alphabet at all. Where McCown's shelves ran bone spider to wraith in a ruled line, this wall is a honeycomb of niches, thousands of them, and the names sit wherever a whispered word sends them. Goblin here, Lich, 100 niches away. Wraith and Goblin, somehow crowded into the same niche near the floor. There is no order to find. McCown is here, and his hands are not resting now. They are cupped at his mouth. Up there, he says. I kept everything in its place so I could find it. Here, he speaks a name to the wall. Lich. And a niche far off answers instantly. The whole record there at once. No walk, no descent, no comparing. Here I kept nothing in its place, and I find it faster. I do not look for the name. I speak it, and the niche it belongs to answers. The trick is in the speaking. The same word must always send to the same niche, or the wall would lose track of its own beasts. He lowers his voice, the way you lower a voice for something true and a little dangerous. And sometimes, not rarely, always, in the end, two different names whisper to the same niche. When that happens, the niche keeps a little chain of everything that landed there. He looks at you sidelong. You built the chain on the fourth floor. You are about to build the wall out of it. This is the last thing I have to teach you, and this is the opposite of everything I taught. For floors, I kept order. A tree, then a leveled tree, then a shelf that ordered itself, so that I could find a name by walking to where order said it must be. Forget all of it for one room. Here there is no order. I do not walk to the name. I compute where it lives and go straight there in a single breath. Speak lich, and the speaking itself tells me the niche. The same niche, every time. Because the same word always makes the same whisper. That is a hash, and the wall is not magic. Look closely. It is a thing you already built. An array of niches, and every niche is one of the little chains you forged on floor 4, holding the few beasts whose names happen to whisper alike. You do not need me for the library's shelf last floor. You reach for it and were right to. You do not need me for this one either. The standard unordered map is this wall finished, but I will not let you trust a whisper you have never made yourself. Build it once, and then in the last video, meet the one library built, and know to your bones exactly what it is doing. So, for 5 floors, we have built containers on raw pointers, right? We have worked with a chain, a stack, a cube, a tree, a binary search tree. And then we even reached for pre-built things in the standard library, like set and map, the balanced trees that have already been perfected. Now, this is going to be our last and best build for our arc here, because the thing you build is made out of a thing you already built, a separate chaining hash table whose buckets are your own chain of monsters from floor 4. A hash table is an array of the linked list you wrote on the 4th floor. Now we're going to implement the core motions for this array of linked lists. We're going to be able to hash a key, find its bucket, insert, find, and erase, and rehash if our table gets crowded. Standing room only around this joint. And we're going to meet some new failure modes, collisions, and our load factor that controls them. And then, exactly as the BST we built on floor 9 turned out to be a standard map, we will reach for the unordered set and unordered map and see that we just built it. So this is the second and final floor of the associative structures run. The next floor down is the finale with graphs. So a few things we're going to learn this week. One, you compute where the name lives instead of searching for it. Okay. In this case, we're going to use a hash function that's going to turn our name into a hash code we're going to use a modulo that will reduce that code to a bucketed index. And then we will use that index to go straight to a bucket and not have to compute. So we average out a big O of 1, not big O of log n. That's awesome. We don't have to walk, so our whispering is instantaneous. And 2, collisions in this type of setup are going to be inevitable. Right? We could compute to the same bucket with different names. Now, with more names than buckets, it is going to be a certainty, what we call a pigeonhole. The fix here is going to be chaining. Every bucket holds a list of everything that landed there, so a collision degrades gracefully into the scanning of a shortened list instead of corrupting something. And the list each bucket holds will be our chain that we built in the past, which is pretty cool. Well, let's talk about load factor, which controls our speed and how rehashing protects it. The load factor is simply our items divided by our buckets, i.e. how crowded our table is. If we let that get too high, the chain grows long and our O of 1 degrades toward an O of n. The cure in this case, or the panacea, is to rehash. We double the bucket array and refile every item into a new home. Okay, so that's pretty awesome. And here we just have a couple little diagrams here. Our hash function mixes every character of lich into a big hash code. We mod the bucket count, which folds that into a valid bucketed index, and that is one of our chain of monster lists. Okay. Another thing here, a collision is harmless when it's 1 or 2 names sharing a niche, right? If our collisions pile up, that's when things can become bad, right? Because we kind of get this massive load factor. And essentially, you just quietly decay into a linear scan, which is what we're trying to avoid here. And in this one, we can see a collision absorbed through chaining. Our goblin and wraith both whispered to bucket 6, so the bucket's chain holds both. And to find range, we compute bucket 6 once and then scan the short chain, comparing names until it matches. This last part is our load bearing. Find must compare the name, not just the bucket, returning the first item it sees, which would be goblin in this case, would be a bug. So a single collision costs you a list of 2. That is what a graceful degradation buys you. And here we see the load factor has crept past the threshold, so the table is then rehashed. It doubled the bucket array and refiled every item. The catch here that makes our rehash honest, each item recomputes its home against the new bucket count. So we have hash mod 8, not hash mod 4, because a bigger array, of course, will send a name to a different slot. The longer chains thus break up, the load factor drops, and the whisper stays a whisper. A rehash that just copied items into the same index would be wrong. Okay. So let's move on over here into VS Code here. Now, let's go ahead and build our executable here and kind of see where we're at. First time building it here. I probably should have built it first before the video started, but hey, we can sit here. It's like awkward elevator conversation, right? Okay. It's very awkward if you're in an elevator with a guy with a night helmet on and you're not like at a LARPing convention or something. Okay. So we have us a new command here, self-test whispers. So let's run that and see kind of what we're rocking here. So you see here we have a lot of failing going on here. Last floor, we stopped building and reached for the library's balanced tree. This floor, we build one more time, and it's the best build in the course because the thing you build is made out of a thing we already built. So it's going to be our hash table. Its buckets are the chain we wrote on floor 4. A hash table, once again, is just an array of a linked list. Okay. So today, all 6 methods are stubbed. So the self-test fails 6 for 6, 1 diagnostic per line. It does not crash and doesn't refuse to build. This is going to be our staircase. So by the last video, all 6 will be green. And notice which self-test failed. Whispers. If we ran self-test BST, for example, right, we're all good. We're off to the races there. Okay. So today we're going to work on our first 3 fail points, and then we'll keep going from there. So let's go ahead and open our hero/hash table header file, and we will get to work here. Okay. Okay, so let's go ahead first of all and scroll to our private members and our two constructors here. Let's see. So you notice here we have a standard vector chain of monster bucket. So this is going to be our bucket array. And then we also have a standard size T. Okay. So what we see here is we have two members. First, and this is the whole floor in one declaration, buckets is a standard vector of chain of monster, an array of our floor 4 linked list. Each slot in the array is one chain holding every monster whose name whispers to that slot. Second, which is our count with the underscore at the end there, is just the number of items. So our size and load factor are instant. And then for our constructors, what we'll need to do is scroll up to our hash table. Probably going to be up here. Yeah. So we see here with our constructors here, for our constructors, the default one sizes the array, and notice the question mark colon that's happening here. If someone asks for 0 buckets in this case, we give them 1 because in a minute, our bucket index is going to do percent of bucket count. And of course, we can never divide by 0. The second constructor is our hook. It walks McCown's bestiary, notice that, in file order and calls insert once per monster, or in this case, it'll be 15 times because we have 15 monsters. Right now, our insert is stubbed to do nothing, so the loop runs and stores nothing. Size is 0, and that's the self-test first failures. So let's make a name turn into a slot. So the first thing we need to do is find our hashKey stub, which will be right here. Okay. So what we want to do for this one is say standard size T of H is equal to 0. We'll say for char C, loop iterating through the names. We're going to say H is equal to H times 31 plus static cast unsigned char C. And outside this, we'll return back our H. Okay. Now, this is the headline really of the whole floor. We are writing a hash function for a string. We start an accumulator, H, at 0. We walk every character, and for each one, H equals itself times 31 plus the character. 31 is the classic small prime multiplier. It's what Java's string hash code uses. Any small odd prime works. The magic is the multiply and add factor. It mixes every single character into the result, so two similar names, Wisp and Wraith, come out wildly different numbers and land far apart on the wall. That's what a good hash does. It scatters. Two details here. The static cast to an unsigned char matters here. A plain char can be negative, and folding a negative in scrambles the math the wrong way. And the multiply will overflow on a long name. That's fine. That's expected. A size T just wraps around, and the wrapping is part of the mixing. Hold the contrast here for later. Grix's hash returns the name's length, which sends every 6-letter beast to the same slot. You'll see why that's a disaster in the last video. This returns the raw code. It is not yet a slot, though. So the next line here is going to turn it into one. So we need to go down to our bucket index code. Okay. And then for right here, we're going to say standard size T bucket index. We're going to say const standard string reference to a name. Oh, whoops, I'm just typing the header again. Oh, sorry about that. We need to fill in the body. What am I doing? We need to return hashKey name mod buckets dot size as such. So this is a one-liner, and it's where the compute where the name lives becomes literal. The hash code is some enormous number, millions, billions, and we have maybe 8 buckets. So we take it modulo the bucket count, The remainder after dividing the number of slots, which is always a number from 0 up to bucket count minus 1, gives us a valid index every time. That's the modulo hash, which is something that you'll read about even in other textbooks and even like the book we use for this class. The trap of the day, and this is something to watch out for, it is percent bucket count, never an unchecked index. Okay, so if you forget the modulo and index with the raw hash code, you fly off the end of the array. And remember, the constructor guaranteed at least one bucket. So this percent can never divide by 0. Now we need names to compute numbers, numbers to compute slots. Let's actually put us a monster in a slot. Okay. So we'll go to our insert stub here. Okay. And for this one, we're going to say bool insert. Oh, that's the header again. Man. It's after 4th of July weekend, right? I'm moving a little slow here. We'll say standard size t I is equal to bucket index m.name, our monster name, buckets bracket I dot push back m. We'll increment the count, and then we'll say return true. Okay, so really 3 lines happening here. We'll add to this twice more in this floor. We compute the home bucket with our bucket index. We index into the bucket array to get that one chain and push back the monster onto it. And notice that's our chain's pushback from floor 4. The structure is composing right here in front of you. We bump the count and then return true. That's enough to make the wall fill up. 2 things we are deliberately not writing yet. First of all, this version doesn't check for duplicates. We insert the same name twice and we get it twice. So we'll fix that in the next video. And it doesn't call rehash to grow when it's crowded, which we'll fix in the 3rd video. But for today, we're going to compute the slot, drop it in, and we will build it. Okay. Okay, so let's go ahead and let's build our executable here. Oh. It's like, yeah, that's a problem here. Let me take a look at this. Okay, so I was telling you earlier about making sure we do modulo here. Anything look wrong here to you? Yeah. Okay, modulo. There we go. Yikes. All right, so we replace that ampersand with a modulo operator. And now let's see if we... There we go. Okay. Okay. So what we should see here, after doing this, is that phase 1 is green. Our hash key is now deterministic and distinct, and our bucket index stays in range. Phase 2 still fails, right? It needs find, which will be in the next video, so don't worry about that. Phases 3 through 6 will also be handled in the 2nd and 3rd videos. The real payoff today is the debug verbs, and let's see if we can watch a name turn into a slot. If you notice, we have should have a hash command in here. Yes, hash command. So we should have this hash command here. So let's go ahead and let's say hash lich. As you hear, boom, hash lich. Boom, we get bucket 2 of 8. So that's pretty awesome there. Okay. Now, one important thing to know here, right, is we're kind of stuck within this 8. Right now, we have just a basic insert happening right now. We have no rehash, so our table never grows past its starting 8 buckets there. Okay. So if we have a thing here, our data, no matter what's just going to fold down into one of them. Okay. The point here is, you may get a slightly different number on your machine, but the point is just the shape here. Okay. Awesome. So let's go ahead and let's also run our buckets. We also have a buckets command I should have up there. So yes, print our hash tables. Let's say buckets. Perfect. So see, I have 1, 2 in bucket 4. We have Marsh Lurker, Necrothal, Rat King, all those guys. So there it is. We have 15 names. Let's see here, double check, make sure we got all 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Perfect. Okay. 15 names scattered across the slots. And look, we have some that have multiple names in it. So we have some collisions happening here. Two different names, maybe whispered to the same niche. And the buckets chain there is going to be holding both of those. That's not a bug. Remember, with 15 names and 8 buckets, that's a mathematical certainty. There's more pigeons than there are holes for them to sit in. And notice our order here. Notice that this is a scrambled order. It's not alphabetical. Last floor, our names came out sorted because a map is a balanced tree. Here, order is just gone. That's the price of the instant whisper. And we'll name that trade out loud in the last video. Okay. So let's go ahead and make sure you commit that, and then I will see you all in the next video. I hope this was enjoyable, and I'll see you soon. Bye-bye.